this is the lecture 5 of module 3 on neural control. The topic today is adaptive neural control for affine systems. This lecture would be a little more involved mathematically. As usual, the control system is always deals with mathematics because of stability analysis and so forth. So, I would request all of you to be patient and attentive to this class. Last 3 classes we focused on indirect adaptive control scheme, but this class today will be on direct adaptive control scheme using neural network. The earlier the indirect adaptive control scheme was very generic, can be applied to any nonlinear system, but today we will be only confining to a specific class of nonlinear system, which is affine system. Okay. So, adaptive neural control for affine system, and also today we will be only focusing on single input single output system. So, topics to be covered today is single input single output affine system, feedback linearization technique, what is meaning of feedback linearization, direct adaptive control of a single input single output system of the form x dot equal to f x plus g x u. This is actually the affine system, and for controlling this we can always assume g x to be known and f x is unknown. This is the first case. Second case is when both f x and g x are unknown, which is obviously more difficult to solve, and simulation results in summary. So, you say that before we assume f x and g x to be unknown, let us assume what is f x and g x. If f x and g x both are known, then this control scheme is solved using feedback linearization. So, this is the first part we will be talking. So, this is the single input single output affine system. The structure is here given. A large class of single input single output nonlinear system can be represented by following affine system, where x 1 dot is x 2, x 2 dot is x 3, and so on until x n dot is f of x. F is a scalar, but x is a vector of x 1 until x n. Similarly, g again is a scalar, but x here is a vector, and that is x 1 to x n u, and y is x 1. If this is this if any system, any differential equation model of a dynamical system, if represented in this form, this is called affine system. Okay. This is nonlinear because here is nonlinearity and nonlinearity here. So, where x is a vector x 1 x 2 until x n, and we have single input and single output, single input and single output. The control problem, find u, okay, such that x t follows a desired trajectory x d t. Okay. The response of the system, of course, this is n dimensional system. The response is okay. So, given find the control law u such that the x t follows x t desired trajectory. One of the possible ways to solve this problem is feedback linearization technique. What is feedback linearization? In feedback linearization, what we normally do, you see that this is u. So, linearization means what should be the u such that this term will become linear. if I find out the overall system here, this should turn out to be linear. So, now let us take a control input u equal to 1 upon g x minus f x plus k v is some constant into r is the reference trajectory plus lambda 1 e n minus 1th derivative until lambda n minus 1 e first derivative, that means e dot plus x and d dot. So, this is what is x and d dot. If I know x desired, okay. So, I always know what is x dot d, x double dot d, and so on until the last one we write x n dot d, where E is y d minus y. This E, the error is tracking error, y d minus y is the output tracking error, and r, sorry, I told r is the reference here, it's r is not reference, r is e to the power n minus 1 plus lambda 1 e to the power n minus 2 plus so on lambda n minus 1 e. So, you see that if I differentiate this r dot, I get E n plus this term, okay. This whole term plus E n e to the e nth derivative is the r dot. So, the power denotes respective derivative. So, this power denotes respective derivative. Putting this expression of u in the system dynamics. So, if I place this u here, so I bring the control law that I proposed and put it here and simplify this expression, I get x n dot is on the right hand side, and the left hand side is x n d dot. I bring it here this side minus x n d dot, which is obviously minus e to the e nth derivative of e, nth derivative of the tracking error equal to. So, this side you see that g x minus f x is there, and with u you have g x. So, cancels out, minus f x and plus f x cancels. So, then you are only left with k v r plus these terms here lambda 1 e to the e n minus 1 derivative until e first derivative. The closed loop error dynamics becomes, if you see here this one minus E n, if I bring to this side, then this becomes e minus e nth derivative becomes plus e nth derivative, and this quantity, and as I said you this quantity is r dot. Okay. So, k v r plus r dot is 0 or r dot is minus k v r. Okay. So, bringing this term to this side, okay, then coupling this you get r dot. So, r dot k v r is to be 0, and from here we get this term r dot equal to minus k v r. So, which is linear as well as stable. So, this is r dot is minus k v r is a linear in R and also stable, because if I assume k v to be positive, then is stable. So, k v and lambda are positive design parameters. Such design techniques are known as feedback linearization technique in literature, because by selecting such a technique what we try to, through feedback, although the system dynamics is nonlinear, by feedback the closed loop dynamics, closed loop error dynamics becoming linear. Closed loop, this is called closed loop error dynamics. So, this closed loop error dynamics is linear. So, okay. So, we understood by now what is affine nonlinear system, single input single output case. Now, we are talking about that what also we understood what is feedback linearization. Now, we will be talking about the controlling such systems when the functionality, that is f x and g x, these functions are unknown. So, the problem arises with feedback linearization control technique when nonlinear function f x or g x or both are unknown, either f x is unknown or both f x and g x are unknown. In such cases, different function approximators like neural networks or fuzzy systems can be used to estimate these nonlinear functions. G x is assumed to be either positive or negative. This is very important. G x is assumed is either positive or negative, that is, we do not want the g x value associated with u to cross 0 value. So, it goes either it is negative or it is positive, it is not both. So, that is because otherwise you can't apply feedback linearization. Feedback linearization means there will be a term u is 1 upon g x and some term here. So, if g x at some point of time is 0, then control input control is, because this is the structure of feedback linearization. So, g x cannot be 0. So, either it is positive or negative, okay, and it has a finite lower bound. So, now theorem 1 for direct adaptive control. What is direct adaptive control? I have to explain to you. Directive adaptive control means in this case we do not identify the system as a whole, we do not identify the system, rather the objective is how do I select a controller, parameterized controller, and the parameters of the controller are tuned directly as a function of tracking error. Okay. As long as such a adaptive mechanism ensures the stability of the entire closed loop system, we are satisfied, and such a system is direct adaptive control, means controller is directly tuned as per the tracking error, okay, as a function of tracking error. So, you can easily see here. So, this is the direct adaptive control scheme. The first theorem we assume in this first one, f x is unknown and g x is known. So, when g x is known and f x is known, this theorem says tells a controller that will stabilize the system. Suppose that the nonlinear function f x of the affine system is unknown, while the function g x is known. Let f x be approximated as f hat x is w hat transpose phi x using a radial basis function network. Then the controller u equal to 1 upon g x minus f hat x plus k v r plus lambda 1 n minus 1th derivative of error plus so on lambda n minus 1 first derivative of the error plus x and d dot will stabilize the system in the sense of Lyapunov. So, if this is my controller, we can show that the system will be stabilized. Proof of the theorem 1. The output tracking error is defined as E is y d minus y, which is also same as x 1 d minus x 1, where y d is x 1 d is the desired output of the system. Let us define a new variable r known as filter tracking error, which is r is e to the power n minus 1 plus lambda 1 e to the power n minus 2 plus and so on lambda n minus 1 e. So, this bracketed terms are the derivative term. So, this is n minus 1th derivative of error, n minus 2 nth derivative of error. So, you can easily see if I write r dot, then this will be e n plus lambda 1 n minus 1th derivative lambda n minus 1 e first derivative. Okay. So, e to e bracketed n minus 1 is the n minus 1th derivative of e and so on. Lambda 1 until lambda n minus 1 are chosen such that the above system is stable. To achieve a satisfactory tracking result as well as to maintain boundedness of the error and neural network weight vector, the control law u is chosen as follows according to the theorem. This is our control law. You can check here in this control law, this has a feedback linearization structure, that is 1 upon g x, and in the first case we have assumed g x to be known, okay, and also we assume g x is not 0. So, that is either negative or positive, and it has a finite lower bound. Now, you see that this is minus f hat x, this is the estimation, neural estimation of the f x using a radial basis function network. And here if you look at in this particular term, this is my kv r, where r is defined like this, and this term you can see this term is r dot minus e n. This term you can easily see, this is r dot minus nth derivative of e and plus x n d dot. Assume that there exists an ideal weight vector w such that original function f x can be represented as f x w transpose phi x. Putting the control law u in the nonlinear system dynamics. So, what is our nonlinear system dynamics? That is finally x n dot is f x plus g x u. So, now you replace this u here. So, what you get x n dot, then f x is here plus g x, and u is 1 upon g x, and these terms that was inside. Okay. So, doing that, what you get f x, which is w transpose phi x, this is assumed that there exists some basis function, this is some basis function as a vector into w transpose, this weight vector. So, if we sum that, we can always approximate any nonlinear function, that is the assumption. So, w transpose phi minus w hat transpose phi, this is this comes where you see that g x cancels out. So, remains minus f x hat. So, this is minus, and f x hat is w hat transpose phi, where we are trying to update what is this w hat. Now, we have to find out a law by which we have to update this w dot w hat plus k v r plus k v r is here plus lambda 1 e n minus 1 plus dot 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 lambda n minus 1 e first derivative, which is already here x n d dot. So, if I now bring this x n to this side, okay. So, x n d dot minus x n will be here we can write this is e to the power n. So, e to the power nth derivative of e is x n desired minus x n dot, x n desired dot minus x n dot is nth derivative of E. You can see that, and then what is happening, minus x n dot. So, this is E n. So, E nth derivative of E plus lambda 1 E n minus 1th derivative and so on. So, this total quantity is actually R. So, what you have now, W transpose phi minus W hat transpose phi plus k V R plus sorry, this is R dot is 0. Okay. So, this is what we will find now. So, defining W hat W tilde transpose is W transpose minus W hat transpose, we can write the same expression which is R dot is, you can easily see that earlier we saw that this is k r plus r k v r, this is k v r plus R dot, and this is W tilde transpose phi. So, that is exactly is here. So, R dot is minus k v r minus W tilde transpose phi. So, whatever we did earlier. So, just to summarize, so we define this. So, x n dot becomes W tilde transpose phi k v r into this. You bring in x n dot to this side, or you can take to the other side also, this side, and then you can write that this is E to the power nth derivative of error is minus W tilde transpose phi, this k v r will go to the other side minus k v r, and these all these terms. Differentiating R with respect to time, you get R dot is this quantity. Substituting E n with into the above equation, this is so you get this entire quantity, and finally R dot is minus k v r minus W tilde transpose phi, but it can be simply also done. So, proof of theorem. Now, how do we show that this table? You see that what is the problem? Problem is here this we have to find out a law, stabilize the system. So, let f x, then the control law will stabilize the system in the sense of stabilize if W dot is some, we have to find out. Here there is a little mistake in this theorem, that we have to find out actually what should be the W hat, this W hat which is there, which is this function is approximated by a radial basis function network, and then weight has to be updated. So, what is that update law for the weights such that this control law will stabilize? This is the question. So, choose a Lyapunov function candidate V x t such that V x t is positive definite, V dot x t is negative definite, then the system is asymptotically stable. Now, consider a Lyapunov function candidate for this system, this affine system is V is half R square, this is the filtered tracking error, R is filtered tracking error, plus half W tilde transpose F inverse W tilde, where F is a positive definite matrix. The derivative of the Lyapunov function is V dot equal to R dot plus, you can easily see 2 cancels out R dot, red derivative of this function. This is my Lyapunov function, I am trying to differentiate this with respect to time. The first term is R dot plus W tilde transpose F inverse W tilde dot. Okay. So, this F is some positive definite matrix, this F, you do not have to worry about that, you can take any positive definite, simply even the identity matrix will do. Since R dot is minus k v r minus W tilde transpose phi, which we have already derived, the above equation becomes V dot is R minus k v r minus W tilde transpose phi. Okay. So, this r dot is multiplied here and then this term. So, since w is constant, you can write w tilde dot is simply minus w hat dot. So, this w hat is actually the actual weights of the radial basis function network that is supposed to be approximating what is f x. Now, v dot is minus k v r square minus, this is your minus k v r square, this is minus k v r square and minus w tilde transpose phi r. So, this is what is there, minus k v r square minus w tilde transpose phi r, and the last term which is w tilde transpose f minus, earlier it was w tilde dot plus. So, w tilde dot plus w tilde dot is minus w hat dot. So, that is why this minus is coming and this is w hat dot. So, if you I can club these two terms as w tilde transpose phi r plus f hat w tilde w hat dot. So, what we need is that the system will be stable if the rate derivative of the Lyapunov function is positive definite, sorry, negative definite. For that, if I can cancel this term or if I can make this term to be 0, then v dot can be minus k v r square. To that happen, this term should become 0. Okay, this is what. And the from here w hat dot is minus f phi r, okay, which provides the update law for w hat. Using this update law, v dot turns out to be v dot is minus k v r square. So, this gives us stability. So, the stability comes when w hat dot, the rate derivative of the w or the weight update law for the radial basis function network, that is approximating the f x, the unknown f x, should be f phi into r. So, if you go back, so I asked this question that this will stabilize the system in the sense of Lyapunov if w hat dot is f phi r. Okay. So, this is the answer. So, sorry, this is a negative sign is also there. So, this is minus f phi r. Okay. So, we completed the proof of the first part. Now, we will go to the second part. This is also there that Barbalat's lemma you can apply, then v dot tends to 0 as t tends to infinity, then r vanishes with t. Since r is this function represents a stable dynamics given lambda 1 and lambda n minus 1, they are all positive quantities, the output tracking error E t will also vanish with t. This completes the proof. Remark, direct adaptive control of single input single output systems is easily achievable when f x is unknown and g x is known. Now, direct adaptive control is unknown f x as well as unknown g x. So, it is difficult to achieve closed loop stability when both f x and g x are unknown. G x is assumed to be lower bounded by known constant g l. An additional sliding mode term is added with the control input to maintain the closed loop system stability. Theorem 2, given that both nonlinear functions f x and g x of the nonlinear systems are unknown, let f x be approximated as f hat x is w hat transpose phi x, that means f x has been approximated by some neural network, radial basis function network. This is different than system identification, because here we assume that a specific neural network is approximating, but we are not identifying what is f x, and g x be approximated as g hat x is p hat transpose psi x, This is again the weights of another radial basis function network represented by P using two radial basis function networks. Let U1 be a control law, some control law like earlier the first part that we showed for unknown f x, but known g x, where 1 upon g hat x minus f hat x plus KVR plus this tracking error terms plus x n d desired trajectory x n dot desired, and U 2 is a sliding mode term which is given as g hat absolute term by g l is the lower bound of g. U 1 we assume that g l is also known. U 1 is the magnitude of absolute magnitude of U 1 signum sine function of r. Then the control law u equal to U 1 plus U 2 will stabilize the system in the sense of Lyapunov, provided if the weight update law for this for the approximating f x w hat dot is minus f I r and p hat dot is minus g psi U 1 r. Okay. So, this part is missing in this slide. So, please note, kindly try to understand this what is this theorem means. Theorem means that we are given an affine system, both f x and g x are unknown. F x is approximated by one radial basis function network, not in terms of system identification. Simply we say that okay, this is representing that, and g x is by another radial basis function network. Then the control law U 1 and U 2 which are defined here will stabilize this affine system. And what is that this affine system? If w hat dot is minus f I r, where f is a positive definite matrix, and p hat dot is minus g psi u r r, sorry U 1 r, this is U 1. So, U 1 r, where g is again another positive definite matrix, phi is the basis function for approximating f x, and psi is the basis function for approximating g x. So, proof of the theorem 2, it's similar way. Again assume that there exists some optimal weight w as well as p, such that f x can be exactly written as w transpose phi x, and g x also can be written as p transpose psi x. The control law is u equal to U 1 plus U 2, where U 1 is the adaptive control part and defined by this particular term, because adaptive, because here f x and g x are updated. There the weights, this f x is approximated by when w. So, when I put this hat, means I have a update law for w, hence these are all varying term. So, that is why this is an adaptive control law, because these controller parameters are adaptive, so as to make always ensure the tracking error converges to 0. So, again we can do the same, take the control law, put in the affine system, find out the closed loop error dynamics. So, if you do that, this is your x n d dot is this one, can be written in terms of U 1 as this one, combining the expression for x n dot, f x, g x and u, you get this particular term. Since x n dot is x n d dot minus nth derivative of E, I have already shown you that, and nth derivative of E is r dot and this quantity. Actually r dot is E n plus this. This implies that from here you get this particular expression here. And further simplifying, rewriting the above equation, you get r dot is this particular expression minus k here minus w tilde transpose phi minus p tilde transpose psi u 1 minus p transpose psi u 2, where w tilde is w minus w hat, p tilde p minus p hat, the way we did last time. To prove the closed loop system stability, let us consider a Lyapunov function of this type, whereas earlier we considered this to be the Lyapunov function, and because we have again another unknown g x. So, that is again added to the Lyapunov function, and you take the Lyapunov derivative, red derivative of the Lyapunov function, you get r r dot plus w tilde transpose f inverse w tilde dot p tilde transpose e inverse p tilde dot. Substituting r dot into the above equation, you get v dot is r, this is your r dot, this r dot we found out this is the closed loop dynamics, sorry. So, this is your r dot. So, this particular expression if you place here in this, then red derivative of v dot becomes this. Okay. Since w and p are constant, you can always write w tilde dot is simply minus w hat dot and p tilde dot is minus p hat dot. So, now recombining, this is your v dot. If you recombine the red derivative of Lyapunov function, so you get one combination here, one combination. This is intelligently done, so that we can find an update law for w hat dot, another update law for p hat dot, and can make these two terms 0, and that is done by this update term and this update term. So, this is there already in the theorem. If w hat dot is minus f phi r and p hat dot is minus g psi u 1 r, then this is Lyapunov stable, but we have not actually proved, because even if we do that, v dot is minus k v r square minus p transpose psi u 2 r. So, there is an extra term here. So, we found the condition for weight update for that part of the neural network which is representing f x, and the other part of the neural network that is representing g x, and we have two control laws. So, this additional control law which is u 2, due to that, okay, here before I discuss that, here it is the singular avoidance. It is to be noted that u 1 becomes unbounded when g hat x tends to 0, okay, which is very obvious. You can easily see that u 1. So, this u 1 will be unbounded if g at x tends to 0. Okay. So, just to avoid this, because if it becomes unbounded a control input, you can't actuate to any physical system and any unbounded input, it has to be finite and bounded. To ensure that, what we do to avoid this singularity problem, we use the concept of projecting g hat inside a set where g hat is not equal to 0. We modify the update law for p hat in such a way that when the estimate g hat is less than the lower bound g l, and at the same time p hat dot is negative, then we do not update p hat. Thus, the modified update law is p hat dot is 0 when g hat minus g l is less than 0 and psi u 1 r is greater than 0. otherwise it is the normal update law, because this is otherwise, because this u 1 is a very large quantity, the update such an update would destabilize the system. So, using the update law for w hat and p hat, we finally get the rate derivative of the Lyapunov function to be minus k v r square and this extra term which is p transpose psi u 2 r. Okay. And this p transpose psi is actually the actual g which is unknown into u 2 r. So, now how do I ensure that v dot is actually positive negative definite, and in this the u 2 is the sliding mode term written by g hat by g l into u 1 signum r. So, given that this is my final expression for v dot, and it is required that v dot to be negative definite. How do I show it? So, you can easily see r sin r, this term is always positive. So, r sin r is always positive. So, if r is negative, this is negative, so positive, and r is positive, the sign also positive, so it is positive. Now, we have to show that g hat u 1 upon g l is also positive. So, that argument is here. Since it is assumed that g is either positive or negative, and the lower bound g l is known. Okay. So, g l will have same sign as of g. So, this is always a positive quantity. Okay. If g l is positive, g l is also positive. If g is negative, g l is also negative. So, hence this quantity is always positive. Okay. So, this is an assumption again, because we can't solve for in generic case. So, the most important assumption here is that g is either positive or negative. That is the only assumption, that is g should not have value both positive and negative. So, okay. So, the first part this part is positive, r sin r is always positive, hence v dot is negative definite. Since v is greater than 0 and v dot is negative definite, this shows stability in the sense of Lyapunov. So, that r, w tilde and p tilde are bounded. This completes the proof. So, what we proved actually, again I go back, I showed you what we actually proved just now. This is the proof that given a affine system which is x 1 dot is x 2 and so on until x n dot is f x plus g x u. Given this affine system, this u is consisting of two terms u 1 plus u 2, where u 1 is given by this linear feedback linearization term structure. U 1 has a feedback linearization controller structure, but this is adaptive because it consists of two neural networks that are approximating those two networks. One is approximating f x, another is approximating g x, and the other control signal which we say sliding mode term, this u 2, which is this particular term. If we have this u, the control law, summation of these two control law, and the adaptive control law has parameters w here and p here, and the adaptive law is w hat dot is minus f I r, p hat dot is minus g psi u 1 r. If this is the parameters of these two neural networks were updated according to this law, then this control law u equal to u 1 plus u 2 will stabilize this system, that is this will be Lyapunov stable. So, this is very important. So, what we discussed today is a very generic understanding of a direct adaptive control of a affine system. Okay. So, now we will validate this controller through simulation. Theoretical validation is already there. Now, we will do the simulation validation before we go for experimentation. For simulation validation, we take a single input single output system where x 1 dot is x 2, this is a second order nonlinear system, x 2 dot is f x plus g x u, y equal to x 1, where f x is given by this nonlinearity which is 4 sin 4 pi x 1 by pi x 1 into sin pi x 2 by pi x 2 whole square, and g x is given by this term. So, you can easily see here g x is a positive quantity. Okay. It can never become negative, it can never become negative. So, we use a sinusoidal trajectory of unit amplitude and 1 Hz frequency as the reference trajectory. Okay. So, reference trajectory x 1 d is a sinusoid trajectory with frequency 1 Hz. Okay. So, that is x d is sin 2 pi t, sin 2 pi t. This is the my reference trajectory, and E is y d minus y, which is x 1 d minus x 1 in state space. When f x is unknown and g x is considered to be known as per our theorem, your E is 1 upon g minus f hat plus k v r x 2 dot d lambda 1 E 1. So, this is our usual control law that we have already defined, and R is first derivative of E plus lambda 1 E. The parameters k v and lambda 1, if you look at here in this controller, the two external parameter, one is k v, another is lambda 1. Okay. So, that is 20 and 15. The number of neurons in the radial basis function network is 30. The centers of a radial basis function network are chosen randomly between 0 to 1. You see that what we are trying to do here, you can easily see that my f x is a function of x 1 and x 2, and g x is a function of only x 1. So, my radial basis function network has two input x 1 and x 2, because I do not know what is g x. So, still I will keep my radial basis function network two inputs to be x 1 and x 2. And the center has the dimensionality 2 by 1, and each of these value is randomly assigned between 0 to 1. The weights are initialized to very small values, that is w, to approximate f x, and the parameter matrix F is taken as identity matrix. So, as you know that our w hat dot, the weight update law for this approximating f hat x, we found out to be minus f phi r, right, and we also took this phi function to be Gaussian function. Okay. So, taking that, you see the tracking is very exact, the desired and actual they almost match, and in fact, the tracking error, the RMS tracking error here is 0.001. RMS tracking error is 0.001. Okay. So, very fantastic tracking here, and this is the control input, that is fade. You can easily see that how the controller is very because it is a nonlinear system, So, the controller is pretty looks like very highly nonlinear term. So, that is when f x is unknown, we assumed, and we assume that g x to be known. Now, we assume both f x and g x are unknown. Okay. So, there in the first part we put radial basis function network for only f x, g x was known. Now, we have to put both f x and g x to radial basis function network, and our controller u is u 1 plus u 2, which is where u 1 is this one, and u 2 is given, this is the sliding mode term. Okay. R, k v and lambda 1 are same as that of previous case. The lower bound of g is set to g l equal to 1. The number of neurons for both RBF network is taken as 30. The centers of RBF networks are chosen randomly between 0 and 1. The weights of the network are initialized such that the initial estimate of g is greater than g l. F and g are taken as diagonal matrices with elements 5 and 1 respectively. Okay. So, and after that when we do this simulation, this is desired and actual, and the RMS tracking error has slightly increased in this case to be 0.005, but you can easily see that in a macro scale you can't see that there is a difference between the desired and actual trajectory. So, the desired trajectory is sinusoid and actual trajectory is also sinusoid. So, and here you see that the controller is highly fluctuating, and also there is a lot of oscillation, and this is happening because, which is expected, because we have assumed that g x is unknown. So, summary: in this lecture the following topics have been covered: single input single output affine nonlinear system, feedback linearization technique for nonlinear system, direct adaptive control of single input single output system of the form x dot equal to f x plus g x u, where f x is unknown when both f x and g x are unknown. To summarize, you learned today a affine system which has a form. In general, an affine system has a form f x plus g x u in general, and one of the most simplified version, if we can still write. So, this is a, here in this case this is a vector, this is a vector, and this is a vector, but the easiest way, even the most simplified affine form, is x 1 dot is x 2, x 2 dot is x 3, and so on. X n dot is f x plus g x u. This is even simpler than this. So, this form is more easy, this is easier to analyze than this form. Okay. Thank you very much.